Hi, thank you for seeing my poster. My name is Maria Fernanda Flores Rodriguez. I'm studying a master's in physics and I'm presenting a work titled Carbon Materials for Efficient Energy Storage and Electrocatalysis. In the current global scenario, with growing energy demand and scarcity of natural resources, the search for advanced and efficient energy materials is a top priority among the scientific community. Among the existing materials, carbon-based nanostructures represent an accessible and reliable option for various energy applications. For this work, broadly two types of carbon are selected: one derived from natural sources and the other from synthetic sources, for clean energy applications like supercapacitors and electrochemical evolution of hydrogen. For this work, we tested 5 porous materials, 2 graphitic carbon nitrates, 2 metal organic frameworks, and carbonized sargassum. The studied MOFs are zeolitic imidazolate structures like CIF8 and CIF67 based on zinc and cobalt respectively. The as-prepared CIF8 and CIF67 samples are carbonized at high temperatures to obtain porous conducting carbons. The graphitic carbon nitrates utilized are GC3N4 and GC3N5. The sargassum is carbonized at high temperatures and activated with potassium hydroxide. The general process for every sample is synthesis, carbonization, physicochemical characterization, and electrode preparation with the prepared samples to perform electrochemical evaluation. For the electrochemical characterization through hydrogen evolution reaction, a 3-electrode system was used to carry out the electrochemical measurements of the as-prepared carbon materials in 0.5 molar sulfuric acid electrolyte. For estimating the hydrogen evolution performance of each of the materials, linear subvoltammetry was recorded in a selected negative potential window from 0 to minus 0.8 volt, using a graphite electrode as counter electrode and a saturated calorimeter electrode as reference electrode. The observed trend in the overpotential is that black platinum is still the material that requires less overpotential to start the reaction, followed by carbonized CIF67 and CIF8, being the graphitic carbon nitrates in the last positions. The Tafel plots are graphed in a logarithmic scale using absolute value of the current density. The Tafel slopes obtained are 2.43 millivolt per dec for black platinum, 61.9 millivolt per dec for carbonized CIF67, and 153.75 millivolt per dec for CIF8. Electrochemical results for activated carbon derived from sargassum for energy storage were obtained using a 3-electrode system to carry out electrochemical measurements of the not activated and activated carbon materials in 6 molar KOH. For estimating the energy storage performance, cyclic voltammetry and galvanostatic charge discharge were recorded in a minus 1 to 0 volt potential window using a platinum counter electrode and a calomel reference electrode. The observed results from both tests show significant improvement in energy storage performance in the carbon derived from sargassum as effect of chemical activating with KOH. This is then confirmed with the specific capacitance calculations. Results show that among the 4 studied carbon materials for hydrogen evolution reaction, CIF67 requires relatively low overpotential and shows a promising Tafel slope, reflecting its highest electrocatalytic activity for her. On the other hand, for the carbon derived from sargassum for supercapacitor applications, an increase in current densities and discharge times was observed after the activation process, which indicates an enhancement in specific capacitance, reaching a maximum value of 185.4 farad per gram. Biomass derived carbon represents an excellent alternative for energy storage applications. Thank you all for your kind attention.